Alrighty, everyone. So we are on page 27, and we're going over topic 1.5. There's a lot we got to cover, and so let's dive into it. Okay? So here's the first idea. This entire topic is about atomic structure, but mostly like what are the electrons doing, and then electron configuration. Okay, so we know that our nucleus is composed of positive protons and neutral neutrons. So overall, this nucleus is neutral, and we got electrons flying around this nucleus. Well, because the nucleus is positive and electrons are negative, there's a force of attraction between them, and we call this an electrostatic force. And Coulomb's law describes that electrostatic force. That if we take the charges of these things, like the charge of the nucleus and the charge of the electrons, and we divide that by the distance between the nucleus and this electron squared, and then we multiply it by a constant value here, then we're able to figure out what the overall electrostatic force of attraction is between them, right? So when you're answering some of these questions, you don't have to ever plug any numbers into this equation, but you can reference it. And I've noticed that graders really like when students say, according to Coulomb's law. And so then they go on to justify the argument. So one could be, according to Coulomb's law, when the charge of the nucleus increases by adding more protons, then the overall attraction to the electrons increase. Or another one would be, according to Coulomb's law, if the distance between the nucleus and the electrons is increased, then that force of attraction decreases. Now, this makes sense, that it's kind of like a magnet, a little negative and positive magnet. We get an attraction between them. And the closer they are, the stronger that attraction is, and the further away they are, the weaker that attraction is. Now, what if I'm analyzing this electron right out here? There's a couple of things going on. The biggest thing that's going on is there's an attraction between this electron and the positive protons inside that nucleus. And I'm showing that with an arrow here. It's like pulling this electron towards the nucleus. But that's not the only electrostatic force. We also have all of these little electrons that push against each other. Because we know when we have two of the same charge, like a negative electron and a negative electron, that they repel each other. So to a lesser degree, we have the other electrons pushing this electron away. If you consider the net of these forces, right? Like if you take the attraction of the nucleus and you subtract the repulsive force of the other electrons, this overall net pole is called Z effective, Z subscript EFF. And Z effective is the effective nuclear charge. Okay? It's given the circumstances of other electrons and such pushing this electron away, how effective is this nucleus at pulling on that electron? Distance also comes into play. Because this is an electron that's further away, its Z effective is less compared to an electron that's closer to it. Great. Now, this is true across nature and definitely chemistry. The lower the energy, the more stable the atoms and the more stable the system. And so if electrons can be in a lower energy level, which is closer to the nucleus, that's preferable. That's a more stable state. But if electrons are forced to be further away from the nucleus than they want to be, then we call that an excited state, that it's not where it's wanting to be. It's less stable. So what if I take two electrons, and the first electron, I'm going to add energy, and I'm going to pull it away from the nucleus, and I'm going to move it from the lowest energy level to the next one. And then I do the same thing with a second electron, and I pull it away, but this time I'm going to pull it away 2 energy levels instead of just 1. Well, the electrons are not going to want to stay there. That when we essentially let go, right? When we aren't supplying that, and that electron is no longer gaining that energy and being pulled away, it's going to want to jump back down to its lower ground state. But in order to do this, it has to lose energy. If it gained energy to move up, it has to lose energy to go back down. The way that an electron loses energy and goes back to a ground state is by releasing a photon. It loses energy in the form of releasing a photon. Now, I have two different comparative examples here. Here is when an electron made a jump from the second energy to the level to the first, and here is where we have a third energy level down to the second. This electron lost less energy than this one. This one lost more energy. And so that would mean that the photon released by this electron has higher energy, and the photon released by this electron has lower energy. And these photons are magnetic photons, like it's the electromagnetic spectrum, which does contain visible light, but it also has gamma, X-ray, ultraviolet, infrared, microwaves, radio waves. And look at the wavelengths. Here is where wavelength is the smallest, and here's where wavelength is the biggest. And you'll notice that energy is the opposite. So when the wavelength was small, the energy was big. And when the wavelength was big, when the wavelength is big, the energy was small. So that's why in my picture here, I drew this as a small wavelength, and this is a big wavelength, because this photon has more energy, thus a smaller wavelength, and this photon has less energy, so thus a larger wavelength. What would we call that? An inversely proportional relationship. This is the symbol for wavelength. So here I have written wavelength is inversely proportional. Okay, so wavelength is inversely proportional to the energy of the photon. The higher the energy, the smaller the wavelength. The lower the energy, the longer, the bigger the wavelength. Now we have a couple of equations that are right on your reference guide about these photons that are released by electrons. Okay? And right here. So I literally just copy paste it, okay? And so it is possible that you might have to calculate some of these things. This first equation is energy is equal to Planck's constant times by frequency. Yeah, I know, isn't that funny that the V is frequency? And it tells us here, it says E is the energy, this V symbol, I think it's like a Greek, like nu or something like that. It's not actually a V, but it looks like it, is frequency, and there's our wavelength. And then we have Planck's constant, which is an H, and that's the number for it. We have C, which is the speed of light, and we have that number, Avogadro's number. Okay, lovely. Now, what if we have an electron that jumps from the n equals 5 down to the n equals 2? Well, this diagram says it will release a photon with 434 nanometers. Okay. What do we got here? Nano means times 10 to the negative 9. So if this is 434 nanometers, that's the same as 434 times 10 to the negative 9 meters. Okay. Now, what if I want you to solve for the energy? Energy is Planck's constant times by frequency. Wait, frequency is not wavelength. Wavelength's not showing up in this equation. But look at the next one. Speed of light is equal to wavelength times by frequency. So what if I do this? What if I divide wavelength? So speed of light divided by wavelength equals frequency. And I plug it in. I get my numbers, and I take the speed of light and I divide it by wavelength, and that tells me the frequency. Well, then I'll be able to plug that frequency in here and get energy. So let's do exactly that. So I'm going to take the speed of light, 2.998 times by 10 to the 8th meters per second. Hey, do you see that -1 meters and then seconds raised to the -1? That is this exact same thing. This is meters, and that's seconds raised to the -1. It just means it's in the denominator, meters per second. So there's my speed of light, and I'm going to divide it by the wavelength. 434 times 10 to the -9 meters. Okay. Now plug that in my calculator, and we're going to see what the frequency is. 2.98 times by 10 to the 8th divided by 434 times by 10 to the -9. So I have a frequency of 6.907, etc., times 10 to the 14th. Frequency is interesting. It has units of hertz, okay, hertz. But hertz is the same thing as inverse seconds, or seconds raised to the -1. Okay, now I'm going to take that number and I'm going to multiply it by Planck's constant. So I'm going to do 6.626 times 10 to the -34 joule seconds, and I'm going to times that by my frequency, 6.9078, etc., times 10 to the 14th inverse seconds. And this gives me my number for energy. Now, sig figs. Here's my starting value. This was 3 significant figures. 4 sig figs for speed of light. Planck's constant, 4 sig figs. So I'm going to go with 3 sig figs of 4.58 times 10 to the -19. Now, this is energy, and energy has units of joules. So there's the energy of that photon that was released. Okay. If you guys have time in class, then we'll probably do one of these. There is a question on the practice problems, which is exactly this, where you take the wavelength and you figure out the energy. All right. This is Schrodinger's equation. It looks really scary. It's not as scary as it looks. But good news is, again, you're not using this equation at all. But you see these like trident looking things. What's so cool is you can plug different functions into that trident, and then it will tell you different things. There's one function you can put in there for electron distribution. And I did this in my upper level chemistry classes. And so we put this electron distribution function in there, and this was the first graph that was given to us. And so what's really cool about this idea is here's essentially the graph, something like that, but now turn and make it 3D. And we get more or less a sphere. And so there's one area that the shape where we're likely to find an electron is spherical, and that's in something called s orbitals. And then we ran it again. We put in a slightly different function here, and for electron distribution, and it gave us this shape. But again, make it 3D, and all of a sudden we got this bow tie looking thing, and that's something we call a p orbital. And then it just continues on. Those are what are d orbitals. This is the p orbitals. That's what the d orbitals look like. And it just got more and more complicated. And so it's so interesting that these areas, these volumes around the nucleus where it's highly likely to find an electron, have all these different shapes to them, and they overlap each other. But it's really, really hard to draw this. And so what chemists did instead is we came up with this idea of an electron configuration. And we have these energy diagrams. And it shows how there are s orbitals, which are the spheres around the nucleus of an electron, the nucleus of an atom, where we can find electrons. So there's p orbitals, those are the bow tie ones. There's d orbitals, these are like clover shaped. And then we also have these crazy things called f orbitals. And each of these boxes is representing one of these orbitals. Something else that we notice is that the electrons were first entering the orbitals that were essentially the closest to the nucleus, the ones that had the lower energy. And so this is the filling order of the electrons in an atom. So what if we have, let's go with, we're going to go with oxygen. And we know that oxygen has 8 protons. And when it's neutral, so this oxygen, when it's neutral, it also has 8 electrons. So I'm going to start filling this in. Couple of rules. One is you have to start with the lowest energy and then make your way up. The second rule is that it's a maximum of 2 electrons in each orbital. We can have less, but we certainly don't have more than 2. And then the third rule is this idea of the electrons they can't be like identical. And so they represent this with something that they call a spin up and a spin down. They were saying, hey, there's 2 electrons inside of this s orbital that's really close to the nucleus, and they call one of them a spin up electron and one a spin down electron. If you want more info about this, come talk to me. There was a cool experiment that they did to kind of give that designation. So we said that there's 8 electrons, but I've only put 2 in. So let's keep going. So there's 1, 2, 3, 4. And then the last rule you need to know is that we have to fill these orbitals separately if they're at the same energy level, like the same amount of energy. We have to fill them separately before we start partnering them. So 1, 2, 3, 4, 5, 6, 7. And then after we have filled all of them with 1, then we can go back and start to partner them, and that would be 8. So the electron configuration for oxygen started with 1s, that's what they filled first, and we put 2 electrons in there. And then after 1s, it filled 2s next, and we put 2 electrons in there. And then from there, we had 2p, and we put 1, 2, 3, 4 electrons in that orbital. This is the electron configuration for oxygen. Okay. I've seen some multiple choice questions, and it was asking, it would say for a certain element, like let's say oxygen. For oxygen, how many of the electrons are paired in orbitals, and how many of them are unpaired in an orbital? And so if I'm looking at this is an orbital that has a pair of electrons, same with that one, same with that one. So there are 3 orbitals that have pairs of electrons, and then there's 2 electrons that are unpaired. And so that's what I saw most commonly, is they would say, hey, for a ground state neutral oxygen, how many of the electrons are unpaired? And this answer would be 2. We can force these electrons by adding energy to make them jump up, and they're going to jump up to the next one. They could go higher if we added more energy to them, but let's say that I added enough energy that I even skipped this like 3s here, and I move, and this guy got moved up there. The electron configuration would be really interesting. It'd be a 1s2, 2s2, 2p3, and then a 3p1. It's not a stable state. It's uncommon, but absolutely possible. It's not going to stay there. It's going to want to jump back down to this 2p level. But if you see a multiple choice question saying, hey, which electron configuration is an excited state and which one is a ground state, this is a ground state because they stayed as low as they could be. This is an excited state because we see that an electron has jumped higher than the lowest that it could possibly be. Alrighty. This is a diagram for Z effective, and so just know that, like I said, the further away an electron is, the lower the Z effective, the effectiveness of the nucleus to pull that electron in, and it's because it's further away, and it's also because the other electrons are pushing it away. Okay. We're going to skip this electron distribution. They've removed those questions, so we don't need to go over that. Yay. So what about using the periodic table to write electron configurations? Okay. Here's how this works. First thing is take helium and imagine with me, and so don't actually like change this on yours, but we're going to pick it up and we're going to move it over here. Okay. And we're also going to write these numbers starting with 1, ending with 7, and that represents the energy levels. And now we're going to represent the orbitals. These two columns together are in the S block. Okay? And that's where we're going to figure out where the electrons are in the s orbitals. When all of these atoms are neutral and in a ground state, their valence electrons, their electrons that are furthest away from the nucleus, are in an s orbital. Other side right here, this is called the p block. P block. Okay, now in this p block, again, these atoms have valence electrons when they're neutral and when the electrons are in the ground state. Then the valence electrons, the electrons in the highest energy levels, the one furthest away from the nucleus, are found in p orbitals. And then this block is called the d block. And we see it contains a lot of transition metals, and we know that some interesting things happen with transition metals. So let me explain through some examples. Let's use the space on this page. Let's write the electron configuration for fluorine. Okay. Here's how I can do that using my periodic table. Here's fluorine, and it's got 9 protons, so 9 electrons when it's neutral. And we're going to start all the way with 1, and we're going to make our way until we get to fluorine. So to get to fluorine, I have to start in the first energy level, and I'm going to enter the S block. So first energy level, I'm going to enter the S block, and I'm going to pass 1, 2 of these spots on my way to fluorine. So it's a 1s2. Then I'm going to keep going. After this 1s2, then next on my trip to get to fluorine is I'm in the second energy level, but I'm back in the S block, and so 2s2. Okay, 2s2, great. Now let's continue on our trip. So here's 2s2. Oh, now I'm entering the P block here. I'm still in the second energy level. So 2p, and then I'm getting to fluorine. So 2p, 1, 2, 3, 4, 5. 2p, 5. So there's the electron configuration for fluorine. Now, what if they asked you how many unpaired electrons are there? What I want you to remember is that s blocks only have one orbital in them. And this makes sense because they can hold a maximum of 2 electrons. So like here's 1s, there's 2s, and all of the p blocks here, these sublevels, these have 3 orbitals. And so within this 2p, we're putting 5 electrons in there. 1, 2, 3, 4, 5. So that would mean that only one of my electrons is unpaired. All right, great. Let's do another one. Okay. We're going to iron, Fe. I'm going to say it first, and then I'm going to write it down. So watch this with me. So I'm starting all the way with 1, and I'm going to make my way until I get to iron, which is 26. So 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p6, 4s2, and then something happens. Whenever you enter the D block, the energy level goes down by 1. So even though this says 4 over here, once you enter the D block, you wouldn't say 4D, you would say 3D. So it's 4s2, 3D, 1, 2, 3, 4, 5, 6. Okay, again, look at your periodic table while I say this one more time. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. Lovely. We have something called the noble gas configuration, or the abbreviated electron configuration. This is unabbreviated. We can also have the abbreviated. And how that works is, if I'm writing the electron configuration for iron, I'm going to find the noble gas, group 18, the noble gas that has the same amount of electrons or less, not more, the same amount of electrons or less, the closest one to it, but that doesn't exceed it. So since this is 26 protons, which means 26 electrons when it's neutral, I wouldn't choose krypton, I would choose argon, which has 18. Instead of starting all the way at hydrogen, I'm going to start right there with argon. And I tell the reader that I'm doing this by putting argon in brackets, and then I keep going. After argon, it's going to be 4s2, and then 3d6. So on the AP Chem test, if they ask you to write the electron configuration, they don't specify, they just say write the electron configuration, you can do either one. But if they are specific, then you need to give the specific one. So if they say, what's the unabbreviated electron configuration, then they want this. Or if they say, what's the abbreviated, then they want this one. Or they could say, what's the noble gas configuration, and they want that one. You can only do this with noble gases. I can't start at any spot and put it in brackets and go from there. I can only do this with noble gases. Alrighty. The last thing that I want to quickly cover, and then Ms. Watts is going to talk about a few exceptions in class, is, what if it's an ion? So what if I turn this iron into an iron 2+? That means that we're going to lose 2 electrons. But I need you to know that electrons are always pulled from the highest energy level. So here is the first energy level. This is the second energy level. This one is the third. It's here plus this guy over there. These ones together make the third level. And in the fourth level, we've only got this guy right there. So I'm going to pull from the fourth level because it's my highest level before I pull from any others. So I'm not going to pull 2 electrons from the 3D. I'm going to pull it from the 4s. And I'm removing 2 of those electrons. Oh, so I'm just like completely removing those. So my electron configuration would be argon 3d6. That the 4s is not even there anymore. Okay, lovely. Practice problems, work hard while I'm gone, and then I'll see you all when I get back.